So the problem given is design a simply supported beam of span 7 meters carrying an RCC slab providing lateral restraint. Okay, so the loading consists of UDL load, where there is an UDL load with a dead load of 100 kilonewtons, excluding the self weight, and a live load of 150 kilonewtons. In addition, the beam is carrying a point load of 50 kilonewtons dead load and 50 kilonewtons live load at mid-span over a stiff bearing length of 75 mm. So here in this kind of problems, it is very important to understand what is the data that is given. So that's the most important thing. So let's write the given data. Given the span of the beam is 7 meters. Okay, and it's a simply supported beam. Okay, remember it's a simply supported beam. They have very clearly said that design is simply supported beam. And providing lateral restraint, right? Providing lateral restraint. So I said laterally restrained beams are also called as laterally supported beams. Laterally unrestrained beams are called as laterally unsupported beams. Okay, so here it's a laterally supported beams. So laterally restrained or laterally supported, they both represent the same thing. And here they have given the loading pattern in a very unique way. So if you observe the question, the loading consists of a UDL. So there is an UDL load. Okay, and this UDL is a combination of dead load as well as live load. Okay, so this UDL is a combination of dead load and live load. So what is a dead load that is given? It is 100 kilonewtons and the live load is 150 kilonewtons. Okay, so the total UDL load intensity is this one, that is 100 kilonewtons plus 150 kilonewtons. Okay, anyways, I'm just writing the data. And here they have also very clearly mentioned that excluding the self weight. So we have to assume the self weight of the section. Okay, I'll tell you how to assume that one a little later. And in addition, the beam is carrying a point load. Okay, let's make it as a concentrated load or a point load. They both are same. So point load. Okay, so again, the point load is a combination of dead load and live load, right? So the point load is again a combination of dead load and live load. What is a point load? That is a combination of dead load and live load. So the dead load value in terms of point load is 50 kilonewtons. And also the live load value in terms of point load is 50 kilonewtons, right? So this is the loading pattern which they have specified. And they have also said that stiff bearing length of 75 mm. So let's make it as bearing length or stiff bearing length, anything is same. So stiff bearing length. So this is usually denoted with B1. Okay, so this is given as 75 mm. And this is the data that is provided. That means you have a uniformly distributed load, right? And also there is a point load exactly at the center of the beam. That's what they have said. So in addition, the beam carries a point load 50 kilonewtons dead load and 50 kilonewtons live load at mid span. Okay, if 7 meters is the total length of the beam, exactly at a distance of 3.5 meters, you have the concentrated load. Okay, so this concentrated load is lying at a distance of 3.5 meters. This is the data that is provided. So the procedure of solving the problem doesn't change except with the factor that you have two types of loadings. Whereas in the first problem, which we have seen, we have only one load, that is the UDL load. Here you have two different loads. So let's see how to solve these kind of problems. So initially, let's make it let's solve for factored loads. Okay, so they have just given the loads, they are not the factored loads. Okay, so for factored loads, again it is subdivided into two types. One is the uniformly distributed load. Okay, in uniformly distributed load you have the dead load. Okay, so the factored dead load is calculated as 1.5 times of what is the dead load in the UDL condition? It is 100 kilonewtons. So 1.5 into 100, which will give you 150 kilonewtons. and there is a live load which is acting as a UDL, right? There is also a live load. So what is the intensity of the live load? It is 150 kilonewtons. So therefore, factored live load is 150 kilonewtons, which will be 225 kilonewtons, right? So this is the factored dead load in terms of UDL and factored live load in terms of UDL. So therefore, total factored UDL load, total factored UDL equals to, it is a summation of dead load and live load, that is 150 plus 225, right? So if you solve for this one, you will be getting as 375 kilonewtons. So this is one of the factored loads. And you have this another factor, which is the point load, right? You also have the point load acting on the member. So you have the point load, which is dead load is 50 kilonewtons. So therefore, factored dead load in terms of point load will be 1.5 times of 50, which will be 75 kilonewtons. And you also have the live load, which is again the 50 kilonewtons. And I'm multiplying with 1.5, which will become the factored live load in terms of point load. So which will be again 75 kilonewtons. So therefore, total factored point load equals to 75 plus 75, which will be 150 kilonewtons. So now here you are very clear that the total amount of UDL load is 375 kilonewtons and the total amount of factored point load is 150 kilonewtons. Okay, so this is how you have to solve the problem. And in the next step, let's only calculate the maximum bending moment. Let's not worry about the shear force now. Let's just calculate maximum bending moment. So how do you calculate the maximum bending moment? So it is very simple that your beam is a combination of the UDL load, right? As you can see here in this figure, your beam is a combination of UDL load as well as point load. Okay, so I am writing the maximum bending moment formula for UDL load as well as for the point load. It will be WL square by 8. So since W is in kilonewtons, I am keeping it as capital W. So capital WL by 8 plus capital WL by 4. So this is for UDL load. Okay, this is for UDL load and this is for the point load. Okay, please be aware of this. So here the value of W with respect to UDL load is 375 and the span is also given, which is 7 meters. So 375 into 7 upon 8 plus the value of W in terms of point load is 150 kilonewtons, which will be multiplying by 7 upon 4. So this value, if you calculate, the answer will be 590.63 kilonewtons meter. Okay, 590.63 kilonewtons meter. So this is how you're going to calculate the maximum bending moment. Why we are doing 2 times? It is because the given loading condition consists of 2 different loads. One is UDL load and the other one is point load. So remember, this is how you have to solve when 2 different kinds of loadings are given on the same member or on the same beam. Now the next step is we need to find out the value of ZpZ required. Right? We have to solve for this ZpZ required. So this will be calculated as, you know the formula, M into gamma M0 by Fy. M into gamma M0 by Fy. What is M? It is the maximum bending moment, which is 590.63. So that is in kilonewton meter. I'm converting into Newton mm, which will be 10 power 6 into gamma M0 value is 1.1 upon Fy value is 250, which will be 2600 into 10 cube mm cube. Now, based on the ZpZ required value, that means based on 2600 into 10 cube value, you are going to select a section. Okay, you're going to select a section from Annexure H of IS 800 2007. Okay, this we have talked in the last class also. So,
Sir, hello.
fine then. So from Annexure H of IS 800 2007. Okay, you have to look at Annexure H of IS 800 2007 and you have to select an appropriate section which has a ZpZ value greater than 2600. So I have solved this problem. So I'm directly writing the section which I have selected. So from Annexure H of IS 800 2007, try ISMB 550. Okay, ISMB 550 at the rate 1.037 kilonewtons per meter. Okay, this section will be appropriate section. So let's also write the sectional properties of this section. So the sectional properties are, so let's write all the sectional properties. Height equals to 550 mm. Width of flange equals to 190 mm. Thickness of flange is 19.3 mm. And thickness of web is 11.2 mm. And the value of I or IZZ equals to 64900 into 10 power 4 mm power 4. Okay, and ZpZ, okay, that is 2711.98 into 10 cube mm cube. See, what is the ZpZ that is required? We require 2600, but how much we are providing? We are providing 2711. So that is in safe condition only. So let's also write the ZEZ, which is elastic section modulus, which will be 2359.8 into 10 cube mm cube. And the radius at root, that is R1, is 18 mm. Okay, these are the different sectional properties of the section. So now what we have to do in the next step, we have to look for the section classification. The section classification. So how do you do the section classification? It depends on table 2 of IS 800 2007. Remember, this table 2 of IS 800 2007 will talks about how to classify the section. However, we know the conditions, that is B by TF should be less than 9.4 epsilon and D by TW should be less than 84 epsilon. If these two conditions are getting satisfied, that is B by TF less than 9.4 epsilon and D by TW less than 84 epsilon, then the section is termed as a plastic section. Remember, most of the times beams will fall under plastic category. Okay, that's the reason why I'm directly taking this one. So here, what is the value of B? B value is taken as half of width of flange, right? So half of width of flange will be, width of the flange is 190 upon 2. So let's solve for this one. So B by TF equals to 190 divided by 2 whole divided by the thickness of the flange. What is the thickness of the flange? It is 19.3 mm. So which will be 4.9. So this value is less than 9.4 epsilon. Remember, the value of epsilon is 1, right? So epsilon is taken as under root 250 by Fi, where Fi value is 250. Therefore, under root 1 will become 1. So I'm directly writing this value as 1. And you have another condition, which is D. Okay. Remember, you know how to solve the value of D. So D equals to total height of the section minus 2 times of thickness of the flange minus 2 times of radius at root. This is how you have to solve. So if you solve for this one, you will be getting the value of D as 475.4 mm. So therefore, D by TW equals to 475.4 upon TW, that is thickness of the web is 11.2, which will be 42.45, which is again less than 84. So therefore, since both the conditions are satisfying, I said when both the conditions are getting satisfied, it will be a plastic section. So the section belongs to plastic category, or the section is plastic. Right? Now here, in this kind of problems, that means when you have more than one load which is given in the question, you have to solve for an additional step, which is check for adequacy of section. Check for adequacy of section. What does it mean? It means you have a section which is carrying an UDL load and also a point load, right? You have a section which is carrying UDL load and point load. That means more than one load it is carrying. So when the section is carrying more than one load, you have to check whether the section which you have selected, that is ISMB 550, whether the section which you have selected is safe or not. Okay, we have to verify that. So in the first problem, we haven't done this check for adequacy of the section because we have looked for only one load that is given. So here, when you have a combination of the loads, you have to solve for this kind of step. That is, you have to check for the adequacy of section. Now here, if you look at the question, they have said that excluding the self-weight of the section, right? So here you have to include the self-weight of the section, right? So any section will have both the self-weight and also the dead load, live load. It's a combination of different loads. So since the self-weight is not given in the question, you have to assume the self-weight. So always assume the self-weight of section in beams. You can take it as 0.8 to 1.03. So it is a typical value. It doesn't, I mean, codebook doesn't say you can take in between this range, but the textbooks follows this method, right? So the self-weight can be ranging in between 0.8 to 1.03. So let us take the maximum value, that is 1.037 kilonewtons per meter. Okay, here you can make it as 1.037. So it's a typical value. There is no provision for this. The codebook doesn't say you should consider only this value. So we are just assuming the self-weight, right? Now, so therefore, factored self-weight, okay, factored self-weight equals to 1.5 times of 1.037. So which will be 1.555 kilonewtons per meter. Now you also have to solve for factored bending moment, which is causing because of the self-weight. Okay, remember factored bending moment, which is causing because of the self-weight. So how do you solve this? You know the formula, that is WL squared by 8. You know the value of W, which is 1.555 into L square is the span, which is 7 square upon 8. Okay, this is for just for self-weight. This entire terminology is for self-weight. And you also have another bending moment, which you have calculated in the second step, which is 590.63, this one. So you have to add this load as well, this bending moment as well. Okay, so which will be 590.63. So if you solve for this one, the bending moment or the factored bending moment is obtained as 600.16 kilonewtons meter. Okay, this is the amount of bending moment that is experiencing by the total span of the beam. So it's a combination of dead load, live load, and also the self-weight of the member. Okay, now you have to solve for ZpZ required. So this is the condition which you have to check. So ZpZ required equals to factored, you know the formula, M into gamma M naught by Fy, right? M into gamma M naught by Fy. So you know the value of M, which is 600.16. So 600.16 into 10 power 6 into gamma M naught value is 1.1 and Fy value is 250, right? So if you solve for this one, you will be getting it as 2640.7 into 10 cube. And remember how to identify whether the section which you have selected is safe or not. it is said that the value of ZpZ required must be less than the value of ZpZ of ISMB 550. What is the ZpZ of ISMB 550? It is 2711.98. So 2711.98 into 10 cube. However, it is mm cube unit. So only if this condition is getting satisfied, then only you can consider it as the safest section. If, for example, this condition is getting failed, then you have to revise the section, right? Go for the next possible section. Okay, that's how the section adequacy is checked. Okay, so in the next step, we are going to solve for the shear force or the maximum shear force. So how do you calculate shear force? Is V equals to WL by 2, right? V equals to WL by 2. So let's write this value. WL by 2. Initially, you have to make it for the self weight. So that is factored shear force will be 1.5 into 1.037, which is 1.55. So I'm directly writing this value 1.555 into L, that is the span, upon 2. Okay. So remember, this is the value for self weight. So this entire term is for the self weight, right? And you also have the value of UDL load, right? So the UDL load is, the total UDL load is 375 kilonewtons. You have to solve for this one also. And you also have to solve for the point load, which is 150 kilonewtons. So again, the same formula, which is W by 2, right? So 375 upon 2, okay, plus 150 upon 2. So if you solve for this one, you will be getting it as 267.94 kilonewtons. So this is the amount of shear force which is coming onto the member. So now the next process remains same. So you have to check for design shear strength. You have to find out the VD value. Then you have to verify whether it is low shear case or high shear case. So let's solve. So design shear strength. Design shear strength. So how will you solve for design shear strength? It is a VD equals to Fi by root 3 into gamma m0 into H into TW. Okay, so you know the value of Fi, which is 250 upon root 3 value into gamma m0 is taken as 1.1 into height of the section is 550 and the thickness of the web is 11.2, right? So if you solve for this one, this value will be 808.29 kilonewtons, right? And you also have to solve for 0.6 times of VD. So which will be 0.6 times of VD value is 808.29. So which will be 485 kilonewtons. Now you have to verify whether V is less than 0.6 VD or V is greater than 0.6 VD. You know these conditions. So V is less than 0.6 VD or V is greater than 0.6 VD. So if V is less than 0.6 VD, it is a low shear case. And if V is greater than 0.6 VD, it is a high shear case. So let's look at what is the value of V here. So it is 267.94, which you have calculated. 267.94. Okay. So here V, that is 267.94, is less than 0.6 VD. That is 267.94 is less than 485 kilonewtons. So therefore, it is a low shear case. Okay, therefore it is a low shear case. So for low shear case, you can find out the value of MD. Okay, so design bending strength MD equals to beta B into ZP into Fy by gamma m0. And since it's a simply supported beam, this value must be less than 1.2 into ZE into Fy by gamma m naught. So how does this formula is coming from? It is coming from clause 8.2.1.2 of IS 800/2007. I have discussed these clauses in the introduction class itself, but however, so anyways, so beta B value is taken as 1 because it's a plastic section. So for plastic section, the value of beta B is taken as 1. So and ZP value, what is the ZP of the I section which you have selected? It is 2711.98. Please check down. So the ZP of the section which you have selected is 2711.98. So anyways, let's write that one. So it will be 2711.98 into 10 cube, okay, into Fy value is 250 and gamma m naught value is 1.1. So if you solve for this one, it will be 616.36 kilonewtons meter. And remember, this value must be less than 1.2 into ZE into Fy by gamma m naught. Let's solve for this one as well. Okay, so which will be 1.2 into ZE value, which is the elastic section modulus. So what is the elastic section modulus? It is 2359.8. So 2359.8 into 10 cube, which is the ZE value, into Fy value is 250 by gamma m naught. And this value, if you solve, it will be 643.58 kilonewtons meter. So obviously 616 is less than 643, right? So it's a safe condition, right? So it's a safe. Okay. And also the value of M is also greater than MD. So it is also in safe condition. The value of M is greater than MD. What is the value of M? It is the factored bending moment, which is 590 point, sorry, not that condition. No, this condition is not required here. Okay. So anyways, so the MD value is calculated and it is in safe condition. So now the next step which you have to solve for is check for deflection. Check for deflection. So you know the permissible deflection and the maximum deflection. What will the maximum deflection? It is delta max equals to L by 300. How does this value is obtaining? It is coming from table 6 of IS 800/2007. Okay, if you refer table 6 of IS 800/2007, there are different categories of the section. Anyways, I'll show you once this problem completed. I'll talk about table 6. But remember, the maximum deflection is limited to L by 300. Okay, this you remember. But I'll let you know how this L by 300 is we are assuming. So the value of L is 7 meters, which is 7,000 upon the value of 300. So therefore, the maximum deflection is obtained as 23.3 mm. Okay. Now you also have to solve for permissible deflection. Okay. Permissible deflection. Now, in the previous problem, we have only one load, right? We have only the UDL load and we have solved it for 5 by 384 into WL cube by 384 EI, right? Sorry, 5 by 384 into WL cube by EA. Now here you have the combination of loads. I'll just go through the first problem and I'll show you. See, you have only the UDL load in the first problem. So therefore you have calculated it for only for the UDL load. But in this problem, which we are solving, it is a combination of two loads. One is the point load and the other one is UDL load. So you have to solve for the deflection value of UDL load as well as the deflection value of the point load. So let's make it that way. So it will be the permissible deflection will be delta total, which will be the total deflection. So how does total deflection coming? It is coming from the deflection due to UDL load plus the deflection due to the point load. PL represents point load. So what is the deflection due to point load? It is 5 by 384 into WL cube by EI. So this is the deflection due to UDL load. And the deflection due to point load is given as WL cube by 48 EI. So this is the deflection due to point load. Remember these conditions. Okay, these are the simple structural analysis concept. So if you solve for this one, you're going to get the total deflection as 7.91 mm. So therefore, the value of delta max is greater than delta total. So that means it's in a safe condition. Okay, so up to here you have an idea, right? Up to check for deflection, you have a very clear idea. Now here you have another concept. I mean, you have to solve for another steps, which is check for, okay, let's make it as a next step, which is check for web bearing. So when you have a combination of loads, remember you have to solve for this step also. When you have only the single load, you don't need to solve. But when you have only the combination of loads, you have to go for this step as well. So it will be given as FW equals to, that is force in web. FW represents force in web equals to B1 plus N2 into TW into Fy by gamma M0. So this value is obtaining from clause 8.7.4 of IS 800/2007. So if you refer that particular clause, you will get to know this formula. That is how the value of FW is obtained from clause 8.7.4. Okay. So now here the value of B1, okay, so that is given in the question, which is as stiff bearing length. Okay, so the stiff bearing length is given as 75 mm. So let's write the stiff bearing length, which is 75 mm. So usually sometimes they might not give you the stiff bearing length. So if they don't give you the value of stiff bearing length, you can assume the value from 75 to 100 mm. Okay, if the value of a stiff bearing length is not provided in the question, you can assume any value between 75 to 100. If it is given, then there is no problem. If it is not given, then you assume the value of B1 in between 75 to 100. Okay, and here the value of N2 is calculated. So it is calculated by using the formula, which is 2.5 times of R1, that is radius at root, plus thickness of the flange. Okay, so this will be 2.5 times of R1 value is 18 mm, which is radius at root, and the thickness of the flange is 19.3. Okay, that is for ISLB, the section which you have selected, ISMB 550. So anyways, if you solve for this one, you will be getting the value of N2 as 93.25 mm. So therefore, the force in web equals to B1, which is 75 mm, plus N2, which is 93.25, okay, into TW, which is the thickness of the web is 11.2, into Fy by gamma M0, that is 250 by 1.1. So if you solve for this one, this value is 428.27 kilonewtons. And you have to verify whether this value is within the safe conditions or not. So how do you verify this one? So it can be verified by using the value of the, which is 266 kilonewtons. How does this 266 kilonewtons is coming? It is not 266, it is 267. So it is the force value or the shear force value. This one, 267.94. So it is less than 267.94 kilonewtons. So if it is less than that value, sorry, it is greater. So if it is greater than that value, then you can consider this as the safest section. Okay, so that's how the check for web bearing has to be done. So just the simple formula, and from that formula you are going to verify this. So remember, whatever the value of Fw you are obtaining, that value must be less than the shear force which you have solved. Okay. So there is also one more step which you have to solve for, which is here it is 8th step, 9th and 10th one. So you have the 10th step, which is check for web bearing. Okay, this also you have to solve. So this you have an idea, but let's just solve this one. So this is obtained from clause 8.7.3.1 of IS 800/2007. If you refer this clause, it talks about the check for web buckling. So here we have a formula which is buckling resistance equals to AB into FCD. So how to solve for AB and FCD, I'll let you know. Okay. So here, before solving, you need to find out the moment of inertia of web. Okay. You have to solve for moment of inertia of web alone. So it will be calculated as B1 into TW cube divided by 12. Remember, this is the fixed formula. What is the value of B1? The stiff bearing length is 75 into T cube. TW is thickness of the web, that is 11.2 into 11.2 cube upon 12. So if you solve, it will be 8780.8 mm power 4. This is the moment of inertia of web. And you also have to calculate the area of web. So how do you calculate the area of web? It is B1 into TW. So the value of B1 is 75 and TW is 11.2, which will be 840 mm square. Okay. Now you have to calculate the value of radius of gyration. Okay. Radius of gyration R equals to, you know the formula, which is under root I by A. You know the value of I, which is 8780.8. So remember, here it is the value of web we are finding. You can make it in this way. That is radius of gyration with respect to web upon 840 is the area of the web. So if you solve for this one, it will be obtaining as 3.23 mm. Okay. Now here you have to calculate another factor, which is effective length of web. So how do you calculate this effective length of web? It is obtained from clause 8.7.1.5. So I'm not showing you these clauses, but you can refer when you have time. So however, if you refer these clauses, you will get to know. So the effective length of the web is obtained as 0.7 times of depth of web. Okay, 0.7 times of depth of web. So if you solve for this one, that is 0.7 times of, what is the depth of the web? It is 475.4. So which will be 332.78 mm. Okay, so this is how you are going to calculate the effective length of web. Now you need to calculate the value of slenderness ratio. So you know the value of slenderness ratio, that is lambda equals to KL by R. So here the L value is taken as 332.78. K value you can take it as 1. Okay, since you don't know the end condition, you can take it as 1. So 332.78 upon R value. What is R value? It is 3.23. Remember, this entire thing we are solving it for web, not for the entire section. Okay, so it will be 102.9. Now here you need to identify which buckling class the section belongs to. Okay, so since that takes too much of time, that means you have to check for a table and you have to find out whether it belongs to a buckling class A or buckling class B or buckling class C or buckling class D. So in order to avoid that entire confusion, you can directly take, okay, you can directly take the table 9C of IS 800/2007 and then you can calculate the value of FCD. So you know I section belongs to buckling class, right? We have the buckling class conditions. So if you want, you can solve, or you can directly take the value of FCD from table 9C. Okay, it's up to you. So if you want, you can cross verify with the answer which I am solving. So from table 9C of IS 800 2007, okay, so from table 9C of IS 800 2007, for lambda equals to 102.9, okay, for lambda equals to 102.9, the value of FCD, okay, after interpolation, everything after you do, the value of FCD is obtained as 103.4 newtons per mm square. I have done the interpolation and I'm just directly writing the value. And you know how to take the values of interpolation. So please remember that one. So here you also have to solve for another one, which is AB. Okay, so AB is taken as B1 plus TW. So AB equals to B1 into TW. So what is the value of B1? So here the value of B1 has to be calculated. Sorry, it is not, not this step. So you have to solve for one more step. So here you have to calculate the value of N1, which is taken as total height of the I section divided by 2. Total height of the I section divided by 2, which is 550 divided by 2, which will be 275 mm. So remember here the N1 value and B1 value in check for web buckling gets changed. Okay, don't take the same values what you have assumed there. Okay, anyway, and here the B1 value, okay, is taken as it is the summation of B1 plus N1 has to be solved, which will be the value of B1 is 75 and the value of N1 is 275, right? So it will be 350 mm. Okay, therefore AB equals to, okay, AB equals to B1 plus N1 into TW. So what is the value of B1 plus N1? It is 350 into TW is 11.2, which is the thickness of the web. So which will be 3920 mm square. Now you can find out the buckling resistance. Therefore, buckling resistance equals to, you know the formula, which is AB into FCD. The value of AB is 3920 and the value of FCD after interpolation is 103.4. So if you solve for this one, it will be 405.3 kilonewtons. And remember, this value must be greater than the shear force which you have solved. What is the shear force value? It is 267.94. 267.94 kilonewtons. So therefore, it is safe. So this is the entire process of solving a laterally supported beam when you have more than one loading condition. So here you have the dead load and also, here you have the point load as well as the uniformly distributed load. So when a combination of loads are given, you have to solve for these two additional steps, that is check for web bearing and also, this is not, both I have written as check for web bearing. This is not check for web bearing, it is check for web buckling. So please correct this, it is check for web buckling. Okay, so you have to solve for check for web bearing as well as check for web buckling when you have the combination of two different loads, or two, or it can be more than one. It need not be two alone. It can be a combination of UDL load plus point load plus point load. Okay, now by using this problem, right, the process which I have solved in this problem, you can solve the third and fourth problems. That is, these two problems can be solved on your own. So just give it a try. If you are not getting, let me know. I'll clarify where you're not getting. Okay. So this is the entire design process of the laterally supported beam when two different loading conditions are provided.